And we move to the next speaker, Ram, who, if you want, you can start sharing your screen.
Hi, thank you. Thank you, the organizers. I'm very happy to participate in this event. And right, yeah. Good. So as we all know, with current technology, whether it's ion traps or cold atoms in optical lattices, superconducting circuits, it's possible to build quantum simulators and computers, but they're a bit noisy. And but in principle, they may provide answers that we cannot classically compute. So one of the questions I'm interested in is, can we test a device that we cannot predict its output? Sure, we can test it on simple cases we can simulate or we know the answer, but can we trust it when it really utilizes the quantum advantage? So with respect to the possible errors, there are two main types of errors that can take place. One of them is a coherent error, where essentially the evolution is unitary, but that is, the system is well isolated, but the unitary is different from the one we want. The other type of error is incoherent error, where due to non-negligible coupling to the environment, the evolution is non-unitary. So this could be either unital error, like decoherence, or it could be non-unital, like spontaneous emission or other heat leaks. There are also other types of error, like reader error and initial state preparation error, but these can be usually quite easily addressed. The standard technology methodology, for example, randomized benchmarking, requires to create dedicated circuits for the diagnostics. And also it cannot separate between these two types of errors, coherent and incoherent. And this is crucial because they are treated in a completely different way. More than that, some information on the circuit is needed. So it's not a black box kind of a test. More specifically, in this method, randomized benchmarking, the key element is that given a certain circuit, you also implement U-1 or U dagger. And if the implementation is perfect, then this will be equal to the identity. And therefore, this expression, which is the survival probability, will be equal 1. But one can show using a very simple example that I will not go through, that this method is sensitive to systematic unitary error. And more than that, it's not a black box test because we need to know the circuit in order to build the inverse circuit. So we aim to detect only errors that cannot be fixed by unitary calibration of the gates. That is coupling to the environment, essentially. There have been attempts before to use thermodynamic approaches for diagnostics. So there is a paper that utilizes fluctuation theorems, and another paper by Michele Campisi that use thermodynamic uncertainty relations. And we also have some experimental paper. Actually, all these papers are experimental, where we use passivity-based approach, global passivity and passivity deformation. The problem with thermodynamic approaches is that they cannot detect dephasing, which is a major error mechanism in these devices. Secondly, they do not work where the initial state is pure. And to create thermostates, sometimes it's very resource consuming. For example, in the IBM processor, it starts in a ground state. And if you want to create the thermal ensemble, essentially you need 2 to the power of number of qubits to simulate a thermostate. So that most of the experiment actually is dedicated to create the thermostate. So the setup of our method is the following. Given some unitary or a circuit, which is unknown to us, we run n different experiments. In the first experiment, we started some known initial state. It could be mixed, but you can think about it as pure, for example, the ground state. And then we measure, after running the circuit one time, we measure the survival probability. Then we do the same after we run the cycle twice. Again, measure the survival probability in the end, and so on after we have, and we stop once we have capital N survival probabilities. So our first finding is that if we look on these numbers, the survival probabilities, they satisfy these inequalities. It's a family of inequalities. So for each, okay, this N should be capital N. For each number of cycles, there's a different inequality. And these WK have alternating sign. All in all, they sum up to 0. And in absolute value, they equal 1. Another finding is that if we look on this series of numbers, they have to monotonically decrease. Okay, and that will be important later on. Our second finding is that if the survival probability changes slow enough, and this will be defined later, then these numbers, okay, these that appear in the inequality, satisfy exponential decay. And this is quite universal. The coefficient here depend on the circuit, on the action of the circuit, and the prefactor depends also on the initial condition. But of course, if you take a log plot, then this simply raises or lowers the graph. All the information is here. The only thing we assume in order to derive these inequalities is that we have periodic unitary evolution. Now, here I listed the first few inequalities, and there are many others, but this specific family has some nice features. And if experimentally we measure that some of these coefficients are negative, then it implies that either the evolution is unitary but not periodic, so we have a certain defect because maybe our control is not ideal and we can't implement the same circuit time after time. Or it could be that the evolution is perfectly periodic, but it's not unitary because there's some external coupling to the environment. And of course, it could be that both scenarios takes place. So a violation of these bounds indicate that there is a certain imperfection in the device. Although I will not show it here, it's not just a yes/no question. You get a number that if the circuit is ideal, it should be 1, and the deviation from 1 can tell you how good the circuit is. So here is an example that we did on the IBM quantum computer, just to demonstrate that we can do heat leak detection with pure state, that, as I mentioned earlier, you cannot do to the best of our knowledge, with any other thermodynamic framework, because they simply become trivial. They are always satisfied, even in the presence of a heat leak. So here we have a controllable qubit that acted as the environment. We have our circuit. And if you want more details, please go to this quarantine thermo talk. Let me just mention that we used just 2 cycles, and we discovered that we are actually coupled to the environment. This is shown here by the violation. And if we decouple the environment, we got positive value as expected. What's actually nice in this specific circuit, you can see it's a classical circuit in a sense, just essentially a C0, okay? And if we put classical inputs, we cannot detect the heat leak. We get just positive values. But if we put state which has quantum superposition, we do get a violation. So that's an interesting aspect of using quantum states for diagnostics. But of course, the goal in the end is to detect intrinsic heat leaks of the devices themselves, and not to use these simulated environments. So this is what we did next. And there are 2 ways to observe violation with these inequalities, actually more than 2. But this is related to our first finding. For example, in the Santiago processor, we got this result that after, sorry, this is the value of Sn, I forgot to type. That after 18 cycles, we already become negative. The width correspond to 3 sigma, plus minus 3 sigma uncertainty. Okay, so this is the first point where we are beyond the uncertainty margin. And it turns out that even though the violation takes place only after 18 points, it's enough to measure only 9 points. And I will explain it later. And another way of detecting a violation is to use the fact that this series should be monotonically decreasing. And what we see here, we don't have negative values in this processor called Raam of IBM, but we do have a violation of monotonicity. So this is the first point, according to the uncertainty, that we can say that it's actually rising. And in this case, only 23 data points were actually needed, even though we have more points here. So this is what I want to explain now. If we look on this series, and then we have more than just a few cycles, it turns out that these coefficients WK decay Gaussianly. So so the tail of the sum actually typically doesn't contribute at all to the sum, and therefore we can clip it roughly after square root of n data points. And we have this estimation for how big is the error, and it goes like the error function, the complementary error function. And just to give an example, if we want to evaluate the inequality for 1,000 cycles, and we want the error to be anywhere between 10 to the minus 3 to 10 to the minus 8, then we just need to take between 64 to 126 data points. So this corresponds to this, and this corresponds to this. So here you can see this extrapolation in action. In this experiment, we took only 70 points. So we really, this is earlier data that we had. We didn't aim for long cycles. We didn't know about this extrapolation. And here we don't see any violation, not of monotonicity because of the uncertainty. And also we don't have negative values. But we can use this, interpolation. And what you see in the blue band here is if we use all the points we have to do the extrapolation, and we get that after 125 roughly, we get a violation. We get negative values. But using all 65 points turns out to be an overkill. And even if we use just 28 points, this is what you see in the red band, then in this regime, the deviation is not observable. So one can actually use less points than what one initially estimate. Now I want to talk about the second finding, which is this universal behavior in the small action limit. So if the series behave like this, and we take the land, then of course we expect an exponential decay. And this part that depends on the initial condition will just move the graph up and down. We ran this very simple 2-qubit circuit. And in green, you can see the simulation. And we ran the same circuit on different processors. So with our answer, it goes to minus infinity, which essentially means that we cross 0 and go to negative values. So this is a violation, negative values. Melbourne doesn't show any violation. It's all positive values. And more than that, it's still monotonic. However, it's not exponential. And we are in the weak action limit. So just by the fact that it's not exponential, we know that it's coupled to the environment in a non-negligible way. However, a different processor, Raam, seems to be following this exponential line very well, as you can see here. It doesn't look like what we predict from the theory, and this actually tells us that it's a good unitary, but just not the one we thought we intended to. Okay, so that's a good indication to the experimentalists. You know, okay, I don't have heat leak problems. I don't have dephasing problem. I just need to calibrate some of my pulses and tune the unitaries. Important question is how to tell if you're actually in the weak action limit if you don't know anything about the circuit. So it turns out that there's a very simple way of doing it by just taking the Fourier transform of the discrete Fourier transform of the survival probability. It's important to take a certain window. Okay, this is a signal processing issue, but it's a standard technique. And with that, we see that if there is even a tiny cutoff, this area corresponds to high frequencies and this is low frequencies. If there's even a tiny cutoff here, we see the exponential decay. If we make the action even smaller, we see a very large cutoff. And once this cutoff closes, we start to see this behavior, which behaves like 1 over square root of n. And it doesn't have any meaning. It just comes from normalization of some of the factors. So one cannot get any information from this.
5 minutes, including questions.
Okay, thank you. So a few words on, like, to give you a peek under the hood, how we got this result. So we used Liouville space, where one takes the density matrix and flatten it into a vector, one long vector. And the only thing I'll need for this talk is that if we ask how the density matrix look after n cycles, then we just take the unitary evolution operator in Liouville space, the one cycle evolution operator, and just take the power of n power of it, and multiply it from the left on the vector. Okay, so we always operate from the left like wave functions, and not as we do in Hilbert space. And this is very convenient. And then what we did, it will sound a bit mathematical, but the essence behind our method is to take the evolution operator and also its Hermitian conjugate, and to build a positive operator from them. And there are several ways of doing it, but this is probably the simplest one. And this can easily be shown if we just take the evolution operator and write it as some exponent of some effective Hamiltonian, which is guaranteed to be Hermitian. Then we can write G like this, like 1 minus cosine of Hermitian operator. And since 1 minus cosine is a positive function, it means that G is a positive operator. And if it's a positive operator, it immediately implies that any expectation value of it must be non-negative. Now, this inequality on its own is entirely not interesting. Okay, it doesn't tell us anything new. However, if we take powers of G, it's also any power of a positive operator is also a positive operator. So we immediately get also these inequalities right here. And using a certain property of survival probabilities, that it actually doesn't matter if you use UL or UL dagger, we get rid of all the UL daggers and remain only with UL. And after some algebra, we get that the expectation value of G n to the power n minus 1 correspond to these Sn inequalities. And if we write, so this is about the positivity of them. If we write the spectral decomposition of G, we know that the eigenvalues of lambda has to be between 0 and 1. Then it's just one line to show the monotonicity property, that it has to be monotonically decreasing. And it's another line to show that that in the large n limit, when the number of cycles is large, we should see an exponent. So to summarize, our method exploits pure states initial conditions, and I think this is a certain transition, at least in my interest, from thermodynamic constraints to constraints on pure dynamics, which is less well known and less trivial. The measurable quantity is the survival probability. It can distinguish between coherent and incoherent errors. And also on the process, it unravels some, to us it was unexpected. I worked a lot with Floquet systems and I didn't know that there are constraints and there should be something exponential in the behavior of any quantity. But also it increases the sensitivity of our method, because now we don't need to see necessarily negative values. We don't necessarily need to see it monotonically decreasing. It's enough that we see that it deviates from a perfect exponent, and we can already quantify if this device is good or bad. It's also economic in terms of the number of coefficients that is needed, as I've shown. And the challenges is first to address the large action limit, to try other experimental platforms and then see if we can diagnose different types of problems and associate specific behavior with specific physical mechanisms. And also to develop an open system description, because what we have now is just unitary derivation, and we can talk about deviation from it, but it's not like we have an open system description. This is still missing. Ongoing work. And with that, I want to thank you for your attention.
Thank you very much, Ram. Thank you for a nice talk. We have time for a question. Yes, there is a Q&A from Marco. Do we want to ask Marco to ask the question himself? Okay, so I'll read the question. Does this method allow for the estimation of spatially?
Now I can.
Okay.
I can.
Okay.
Okay. No, just yes. It was just about the spatially correlated errors in the model. If this method allows for the estimation of spatial correlations between the errors on different qubits or something like that.
Right. So that would depend simply whether this error is unitary or systematic, or if it's not unitary.
Yeah,
whether
sorry.
It's a.
I was meaning incoherent errors, so non-unitary errors, let's say.
So okay, can you rephrase the question entirely?
Yeah, let's suppose we have. I mean, we don't know it, but we have in our system some errors that are incoherent, so they are not due to just a recalibration of a unitary gate, but they are spatially correlated in the sense that like if there is a common path acting on qubit 1, 2, and 3.
I understand. So I understand the question. Thank you. There's no intrinsic limitation on any type of error, but of course it's not guaranteed. We don't have for now a certain lemma that guarantees that we can detect any type of error, but it's most likely that it will not show this nice exponential behavior because of this error, but we still can't guarantee. This is also one of the open questions, but there's no limitation whether it comes from single qubit error, 2 qubit error, or higher order interaction. There's no limitation that I know of.
Okay, thank you very much.
Okay, thanks. If there are no more questions, let's thank Ram and all the speakers of today's session. Thank you very much. If Camille or Ilya wants to say something.
Yes. Yeah, I had the question, but maybe I can send an email to Ram. So yes, thank you very much, all the speakers of today, and also thank you very much the chairs, so Felix and Gabriele. And so we still have one session today. I think